In this video, we would like to learn about the Fourier series representation of a continuous time signal. So basically, the target is to learn about the Fourier series representation of a continuous time signal. Uh, Initially our target would be periodic signals, and then we would expand we would like to extend this concept to aperiodic signals as well. So and as I mentioned that in this video we would learn the Fourier series representation of a continuous time signal. We would definitely learn about discrete time signals as well. As you can see this in this equation, a continuous time signal uh, x of t is written as the summation of complex exponentials, right? It's written as a summation of complex exponentials. So if you concentrate on this expression, at the left hand side you have x of t, which is just a continuous time signal, any shape, right? We are not discussing its shape right now. It is a continuous time signal of any shape, right? It should be continuous. And on the right hand side you can see the summation. So there is a basically a summation. So if you observe on the right hand side, we have actually a summation. Let me concentrate over here. It's actually a summation sign, right? So you have a summation sign. We actually have a summation sign. And this summation, if you concentrate on the value of k is the running index, and k varies from minus infinity to plus infinity. So k is from minus infinity to plus infinity. And then you have a sub k, which these actually are the Fourier coefficients. We would discuss details of these coefficients, how to find these coefficients in the successive videos. In next couple, actually I need a couple of videos to thoroughly explain the concept of Fourier series representation. So we would see these these are actually Fourier coefficient a sub k. So in this particular expression we have infinite number of terms in this summation, as k from minus infinity, k is from minus infinity to plus infinity. And then you can see the next term, which is the exponential, e raised to power j k omega naught t. So we would discuss each and every term in this expression thoroughly, graphically, as well as with the help of an example. So the target would be to learn Fourier series representation of continuous time signal in these couple of videos. But before going to actually this Fourier series representation, let me talk about the response of LTI system. The response of LTI system to complex exponential. This would be, if S is complex, we can say this is a complex exponential, right? So e raised to the power st, as we have discussed these concepts in the class as well, e raised to the power st is a complex exponential, a general form of complex exponential. So we would see the response of LTI system, to complex exponential, and with this response you would definitely come to know about two definition which are very important, the eigen function and the eigen value. So you would learn about the eigen function and the eigen value. So let's concentrate on the response of LTI system to the complex exponential, right? So let me move to the next slide. And okay, so suppose this is our LTI system. We have a system. This is our LTI system. You give some input to this system, and we have certain output of the system. Suppose the system input, we represent the input of the system by x of t, a continuous time signal. So we would have the output of the system y of t, and I hope everyone can write the expression for the output of the system. If you write the expression for the output of the system y of t, that is your y of t is actually, suppose this is the response of the system, the impulse response of the system is h of t, right? So you can write the output of the system as x of t convolved with h of t, right? Convolved with h of t. So this is the output of the system, which is the represented as a convolution of the convolution of x of t and the impulse response of LTI system h of t. You can also write the same expression as h of t convolved with x of t, right? We can also write it just the commutative property, applying the commutative property. So if you want to write this expression in the form of an integral, as we have seen several times, that we usually write expression in the form of an integral, we can definitely write an integral for this one. So if you write it in the form of an integral, you can write it from minus infinity to plus infinity h. I'm writing it for this one. So you have to change the variable t to tau, right? And then h of tau, x of tau, and then the next variable is let me write it x of t minus tau d tau, right? And this is actually your y of t. This is your y of t. This is the expression for this convolution h of t convolved with x of t. So you can just compute this integral and you can find out the output of the LTI system with the help of the impulse response, if you know the impulse response of the system. Okay, there is for LTI systems, if you have an input, if you give suppose let me redraw my system here. If I have an LTI system, with an input and an output, if you give a complex exponential here at the input of LTI system, if this is the input of the LTI system is a complex exponential, keep in mind S is complex, right? If when we say S is complex, then it means you can write S in the form of a plus jb, rectangular form, or you can write it as a e raised to the power j theta. It's a polar form of S, right? So if you give a complex exponential to the LTI system, the output y of t is also a complex exponential, but its magnitude is modified here. LTI system modifies its magnitude, and I would write that magnitude as h of s, and that modification, the modification in its magnitude, which I have written here as h of s. Let me rewrite this again. Let me rewrite it again. So if you observe this, let me erase it, and I would rewrite this magnitude with a different color. So the magnitude is modified, and this magnitude can be expressed as h of s. This modification actually is can be written as h of s, which means that it is the modification is there, but it is a function of s. Now you can prove it it's straightforward. as just we have seen that if your input is x of t, you can write the output in the form of an integral. So let's try to solve an integral for this LTI system. So you can see your y of t. Y of t is an integral h of tau and x of t minus tau d tau, right? Now we have x of t, as we saw x of t, or let me write x of tau. If my x of tau is e raised to the power s tau, right? You change the variable t, replace it by tau, just changing another variable tau, right? So if our x of tau is this one, we can write it implies that x of minus tau, you can always say minus tau is like this one, and t minus tau, you can write x of t minus tau. So t minus tau would be e raised to the power s t minus tau, right? S of t minus tau. Now put it in this integral, substitute and compute your y of t. If you substitute it in this integral, you have h of tau, and then you have e s t minus tau d tau, right? You can rewrite it, well, you can rewrite it as e s t minus infinity to plus infinity h of tau e raised to power minus s tau d tau. So you can see, you can always write this one outside the integral. Why you can write this outside the integral? Because e raised to the power st, here we have a variable tau. So everything with the variable tau is it's just treated as a variable, while t is fixed. It's just like a constant. So this term, we can write this term outside the integral, right? So we just wrote the term with t outside the integral, and the rest is inside. Now you can see this integral. Let me erase these extra marks so that you can see the integral. We have e raised to power st. Now I can say, okay, this is actually this one is actually the same complex exponential, right? E raised to the power st, and this is, you can write it as a function of h of s, right? So this is a function of s, because you would always you will integrate with respect to tau, and you are putting the limits of tau from minus infinity to plus infinity. So you would be left with the function of s only. You can try this one as well. You can always try this one. If you put the limits of tau, you would be left with the function of s only, right? We will see with the help of an example. So this basically, this one is h of s. This integral is h of s, and you can see that your output of LTI system is when your input is complex exponential. This one, when this is your input, your output is actually the same input, and with a multiplying factor h of s, which is this is actually some constant. This h of s, you can see it's modifying its magnitude, modifying the magnitude of this complex exponential. And keep this in mind. Another important thing about the complex exponential, I hope you remember that what's actually a complex exponential. We have discussed a lot. If I just if I say that my s of t, when s is pure imaginary, right? Suppose your s is pure imaginary, so we can say j omega, suppose s is j omega naught, so e raised to power j omega naught t. And when your s is pure imaginary, you can see using the Euler identity, you can write e raised to power j omega naught t as cos of omega naught t plus j sine omega naught t. So basically you have two sinusoids, cos of omega naught t and sine of omega naught t. It's a complex exponential, and we have there is a very close relationship of these exponential e raised to power j omega naught t and these sinusoids, both the complex exponentials, right, e raised to power st, or when s is j omega, this e raised to power j omega naught t and cos of omega naught t both are periodic with the fundamental period 2 pi, with the fundamental period which you can see 2 pi 2 pi over t. This is the or you can say 2 pi over t naught. So it's the fundamental period is t naught. Both are actually periodic with the fundamental period t naught. You can say the fundamental period is t naught. So what we conclude that when the input, let me summarize this lecture. When your input is to LTI system is a complex exponential, your output of the system is a complex exponential, the same complex exponential modified by h of s, a function which depends on this s, the value of s, the complex exponential value, and it modifies the magnitude of the output. So if the input is complex exponential, say suppose say the input is sinusoid, the output would be sinusoid, right? But the amplitude would be modified. Well, in now come to the definition of the eigenvalue and the eigenfunction, right? So let me concentrate on these specific value. What's actually the eigenvalue and what's the eigenfunction? Let me concentrate on those based on our discussion right now. So keep in mind, when we give the input as a complex exponential, the output is a complex exponential. Now what's the eigenvalue? Actually these complex exponential are the eigenfunction of the LTI system. These complex exponentials are the eigenfunction. This complex exponential, the function, it is a function when you give input as a complex exponential, your output is also a complex exponential, and this basically this e raised to the power st, this e raised to the power st is the eigenfunction. So a signal for which the system output, now let me summarize it, that the signal e raised to power st is, this is actually a signal for which the system output is a constant times the input is referred to as the eigenfunction. So a signal, this one e raised to the power st, for which the output of the system is some constant times the input, right? So a signal for which the output of the system is basically some constant times the input, that function, that signal is known as the eigenfunction. We call it the eigenfunction. And the eigenvalue, the corresponding value, this value, this is actually the eigenvalue, the amplitude factor this amplitude factor. This amplitude factor is referred to as the system's eigenvalue. So the amplitude factor, let me specifically write this. Let me specifically write it. A signal. Let me specifically write this statement. A signal for which the output, a signal for which the output of a system, the output of a system is constant times the input signal. The input is referred to as the eigen function, as the eigen function. It is referred to as the eigen function, and the amplitude factor, the corresponding value. For example, let me say, for example, e raised to power st in our above example is the eigen function, and the corresponding value, the amplitude factor, and the amplitude factor, is the eigenvalue, that is the eigenvalue. In our above example, for example, h of s, this is the amplitude value, or that constant. It is that constant. Keep in mind, you saw it in the form of an integral, but actually if you solve that integral, it's actually a constant. So we would see with the help of an example the successive statements. Now what we actually learned, that if you have before going to an example, let me talk about the discrete systems as well. If you have the discrete input, for example, your input is in the form of z raised to the power n, which is a discrete input value, right? A discrete signal, a discrete input. So your corresponding output of a discrete time system, it would be again in the form of the summation. It is actually it's the same concept, x of n convolved with h of n, right? H of n, or you can say h of n commutative property convolved with x of n, right? And you can always write the this in the form of a summation. So in the discrete time we have summation for all k, for k minus infinity to plus infinity, h of k and x of n minus k. Keep in mind the running index is k here. Right? So the running index is k here. So your output is the convolution sum of that is the output, and your output would be, if your input is a complex exponential, if your input is a discrete time signal, the output for the output y of n, you would see that the output y of n is actually the same complex exponential, but modified by a constant, and that constant is h of z. That is h of z. So for LTI system, for LTI, and you can very easily prove this one as well. You just put the in the above summation, you just write it in this form. You have a summation k minus infinity to plus infinity h of k and x of n minus k, so z of n minus k, z of n minus k, right? So this is your x of n. So x of k would be z of k, x of minus k would be z of minus k, right? So you just let me write it here. X of minus k would be z of minus k, and x of n minus k would be z of n minus k. So this is what I have written over here, right? This is what I have written. That is what I have written in this equation. And if you solve this equation, if you solve it, what you actually get, you get the summation for all k minus infinity to plus infinity h of k, and you have z of n and z of minus k. Now this z of n, it can be written outside the summation. We can write it here because it's the running index is k. So z of n is just like a constant. Z of n is just like a it's for this summation, it's just like a constant. So we can write it outside this summation. So let me write it outside here, and let me write it outside z of n, and then you have a summation from k minus infinity to plus infinity h of k z of minus k. Now we have the same form. We can see that it is basically your y of n is actually the same input times this constant. So your output is actually some constant times this constant. Can be written h of z times the input signal. So you are in your LTI system. Once again, this is for the discrete signal. If your input is a complex exponential, the output is also a complex exponential. But it has a multiplying factor which modifies its amplitude, and that is this value for LTI system. Now this is actually the eigen, we say it's the eigen function, and this one is the eigen value of the system. Now with this example, we can always extend it to, because we have an LTI system. So suppose your input x of t, is in this form: a1 e raised to the power s1t plus a2 e raised to the power s2t plus a3 e raised to the power s3t. You have three complex exponentials, and your input is the summation of three complex exponentials. So your output would always also be the summation of three complex exponential. And if we try to write the output for this one, for this individual, the output would be, we can write the output as a1 h of s1 constant times the input s1 of t. This is our signal. So if you multiply it with a1, it's with a1 because we have LTI system. So any scaling factor at the input appears in the output as well. Similarly, you have another summation, you have another term here, and for this one the output of the system would be a2 h of s2 e raised to the power s2 of t, the input signal. And for the third one, which is this one, we have another a3 h of s3 e raised to the power s3 t. So the output is also for the, if the input is the sum of exponentials, the output is also the sum of exponentials, the same exponentials, the same sum of the same exponentials, and those exponentials are modified by constants, and these constant depends on these complex values s1, s2, s3, and the same scaling factor which appears in the input, it also appears at the output, right? So if you have something at the input, it would appear in the output, right? Anything in the input is available in the output. So this is for LTI systems. In general, you can generalize this equation and you can write it. Your input in the compact form. You can say, okay, if my x of t is the summation of complex exponentials s k t for all k. This is for all k minus infinity to plus infinity. Then my output would also be in the form of summation for all k, and it would be a k h of s k e raised to the power s sub k t. So if the input is the summation of complex exponential, the output of LTI system is again the sum of those complex exponentials, the sum of those complex exponentials which appear in the input. The magnitude of each exponential is modified by a constant which depend on sk, right, for any k, and there is a coefficient ak here, which is a scaling factor. We would see with the help of an example. That how LTI system respond to these complex exponentials in the next video.